This is the final lecture on sorting algorithms, and we'll be discussing the Radix sort and counting sort algorithms, both of which are quite different to the sorting algorithms we've discussed previously in this chapter. So let's start our discussion by considering how we would go about sorting a pile of books. Well, what we could do is we could attempt to sort the books by the names of the authors. We could do this then by creating 26 separate piles, and we have one pile for each individual letter of the alphabet. So then what we do is we take all of the books by authors whose names start with the letter A, and those go into the first pile. Authors whose names start with B, all of their books go in the second pile, and so on and so forth for all 26 letters of the alphabet. So now we have our books finally organized then by first letter of the author's name. But of course, there are a lot of authors whose names start with the same letter. So we can't stop at this point. We have to continue with our sorting procedure. So then for every one of our 26 piles, we would then have to sort those in the same way. So we would create then a further set of subpiles, 26 of those, for each letter of the alphabet, and we would do this for every one of our original piles. So in other words, the pile for A would then contain 26 piles, the pile for B would contain 26 piles, and so on all the way to the pile for authors whose names start with Z. So then what we do is for each of these piles, we look at the books that we are attempting to sort, and we select then all of the authors whose names have a second letter of A, and those go into the first subpile. All of the authors whose names start with a second letter of B go into the second subpile, and so on and so forth. So we can just then keep performing this procedure, and we continue doing this until eventually each pile then contains only one author's books. And at this point, we have then managed to successfully sort our entire library of books. Now, it turns out that this is actually a completely legitimate sorting algorithm, and it is in fact used in the real world. For example, a lot of post offices use this kind of approach to sort mail that are sent to a whole city or country's worth of recipients. So can we use the same strategy to sort a sequence of numbers stored in an array? Well, of course, numbers do not consist of letters, so we can't sort them alphabetically. However, they do consist of digits, which we can use to sort them. So what we need then is a separate pile for each individual digit that our number system uses. And because we're working with the decimal base 10 number system, we have digits then that range from 0 to 9, meaning that we have 10 separate digits, and so we need to store 10 piles. All right, so let's see how this would then actually work for an array of numeric values. And we're going to start off then processing the unit digit and then move digit by digit to the right. So this is our array that we want to sort, and we now need to create 10 piles. So we can do this fairly neatly by using an array structure, and the subscript then at each position within the array represents the digit that the pile is for. So in other words, at subscript 0 we have the pile for the digit 0, at subscript 1 we have the pile for the digit 1, all the way through to 9 where we have the pile for the digit 9. Now, of course, multiple numeric values could map into the same pile, so therefore at each subscript we need to store some kind of list structure where we can store multiple numbers. All right, so we said that we would start then with the unit digit, which I've highlighted in red over there. So now we need to look first of all at the value 12, and we see that its unit digit is 1, which means it needs to go into the pile for the digit 1. If we look then at the number 23, we see its unit digit is 2, which means it needs to go into the pile for the digit 2. In a similar fashion, the number 2 needs to also go into the pile for the digit 2. 17 needs to go into the pile for the digit 1. And finally, 100 needs to go into the pile for the digit 1. So now we've finished processing the first digit in all of our numbers, but we see that we have multiple values within a single pile. So we can't stop at this point. So we need to then process each of these piles one by one. So let's start off then with the pile for the digit 1. And we need to here create again another array and then perform the same sorting procedure, but this time for the second digit within the number. So I've highlighted the second digit in each of the numbers in the pile for the digit 1. And then we start off with the value 12. So 12's second digit is 2, meaning that it needs to go into the pile for the digit 2. Then we move on to 17, which needs to go into the pile for the digit 7. And finally, 100 needs to go into the pile for the digit 0. But now we immediately see that we have a problem. If we look at these numbers in the pile for the numbers that start off with the digit 1, we see then that we've sorted these values into an incorrect order. This is not an ascending order that we've created over here. So what this means then is that sorting from the leftmost digit to the right doesn't work, and we need a new strategy. So how can we go about solving the problem that we identified in the previous example? Well, it turns out we can use essentially the same procedure with a few minor modifications, and we will end up with an algorithm that actually successfully sorts an array of numbers. So the first modification that we need to make is to ensure that all of the numbers we're sorting have the same number of digits. And we'll do this by padding each number with leading zeros to make them all exactly the same length. In other words, they will all consist of the same number of digits. Then the second modification that we need to make is that we will sort from the rightmost digit to the leftmost digit instead of from the leftmost digit to the rightmost digit. Now, we also then saw that we need to store multiple values for the pile that is created for each individual digit. So we need to decide on a specific data structure that we will use for the storage of these values. So we'll use then a queue, and we'll have one queue for each digit. In other words, one queue for each pile that our sorting algorithm uses. So also then, if we look at our previous example, we can see that it wastes quite a lot of memory. And this is because there is a separate destination array for each digit. So when we sorted values according to the first digit, then we needed to take each of those individual piles and create then a separate array containing 10 digits. And we also then need to repeat this process as many times as the maximum number of digits that we see within the numbers that we are attempting to sort. So what this means then is we get a huge proliferation of arrays. And obviously this wastes quite a lot of memory, but additionally we also have to then allocate memory for these arrays and eventually deallocate them. So this means that the performance of our sorting algorithm will also take a hit. So we can address this then by moving our numbers back and forth between the array that we're sorting and a single array of queues. So this is then the Radix sort algorithm with these modifications. We have a variable n, and this variable then stores the number of digits in the largest number within our array. So in order to determine this value, we would need to traverse through the array and figure out for each of the values how many digits there are and store the largest number through our entire traversal. So once we've then found this value n, we then need to once again iterate through all of the numbers in our array, and we need to, for each of them, add leading zeros so that all of them then consist of n digits. So once we've now padded each of our numbers, and we know that they all consist of the same number of digits, we then run through this loop over here, and here we have our loop control variable d, and this starts off then with a value of n and decrements it at each iteration down to 1. So this loop will then essentially start with the rightmost digit, and it will move then down 1 digit at a time until eventually it reaches the leftmost digit. Right, then we need to distribute our numbers within our data array among the queues for the digits 0 to 9, and we do this according to digit D. So this is the same distribution approach that we used in our previous example. Once we've distributed all of the values to their appropriate queues, we then run through this final loop over here. And this loop then runs from 0 to 9. So it's running through the piles, starting with pile 0 and ending with pile 9. And then for each of the piles, we dequeue each number that is contained in the queue for that pile, and we add it to the next available position in our original data array. We'll now look at the operation of the Radix sort algorithm by applying it to this example array over here. So the first thing we need to do is ensure that every number in the array consists of the same number of digits. This requires us to pass through the array, counting the number of digits for every value in the array and finding the highest number of digits. So we see then that the number 315 consists of 3 digits, and this is the highest number of digits out of all of the numbers contained in this array. What this means is every other value contained within the array needs to have leading zeros added to it so that they all consist of 3 digits. So that's exactly what we've done over here. If we look at the value 25, we see it consists of only 2 digits, which means we need to add 1 additional leading zero to pad it up to 3 digits. In a similar fashion, the number 5 consists of only 1 digit, so we need to add 2 leading zeros to pad it up to 3 digits. And we do this for all of the other values within the array. Next, we need to create all of our various piles, and we do this exactly the same way that we did in the previous example by means of an array of 10 values ranging from the digit 0 up to the digit 9. Now we need to consider the rightmost digit for every value in the data array, which I've highlighted in red over there. So we now need to run through the data array from the beginning to the end, and for each one of these individual values we need to place the number into the correct pile. So if we consider the value 25, we see the rightmost digit is 5, which means it needs to go into pile 5 at subscript 5 within the array. The number 5 also has a rightmost digit of 5, meaning it also needs to go into the pile for the digit 5. 20 goes into the pile for the digit 0. 315 also goes into the pile for the digit 5. 11 goes into the pile for the digit 1. And finally, 77 goes into the pile for the digit 7. So now we've run through all of the values within the data array and assigned them to piles. We now need to run through our array of piles, and for each particular pile within this array we need to then dequeue the values and place them back into our data array. So if we have multiple values that are contained then within a pile, those are contained in a queue, which means we remove then the element that was added first to the queue. In other words, we remove 25 first, then 5, and then 315. Alright, so starting off then with pile 0, we dequeue 20 and place it into the first position in the data array. Then we move on to the pile for the digit 1, so we DQ 11 and place that into the second position in the data array. Then we DQ 25, that goes into the third position, 5 goes into the next position, and 315 goes into the second last position. We now move on to the pile for the digit 7, and we DQ the only value in that pile, 77, and place that into the last position within the array. At this point, we've finished all of the processing for the rightmost digit. This means we need to move on to the next digit to the left, which I've highlighted in red over there. So now we repeat exactly the same procedure again. We run through our data array and we assign our numbers to the correct piles. So the value 20 goes into the pile for the digit 2, 11 goes into the pile for the digit 1, 25 goes into the pile for the digit 2, 5 goes into the pile for the digit 0, and note here that we are working with the digit 0, which is a padding digit for the number 5. Then we move on to 315, which goes into the pile for the digit 1, and finally 77 goes into the pile for the digit 7. So now we've run through all of the values in the data array. We now need to run through all of our individual piles, dequeuing values as we go and moving them into the data array. So we dequeue the value 5 from pile 0, that goes into the first position in the data array. Then we dequeue 11, that goes into the second position in the data array. We dequeue 315, which goes into the third position. Then 20, which goes into the fourth position, 25, which goes into the second last position, and finally the value 77, which goes into the last position in the array. At this point, we've finished processing the second digit, so we now need to move to the final leftmost digit, which I've highlighted in red once again over there. So again, we perform then exactly the same procedure, moving values from the data array into their correct piles. So the value 5 moves into the pile for the digit 0. Again, note that we are performing that move based on a padding digit of 0. 11 also moves to pile 0, once again based on a padding digit of 0. 315 moves to the pile for the digit 3. 20 moves to the pile for the digit 0, again based on a padding digit. 25 moves to the pile for digit 0, also based on a padding digit. And finally, 77 also moves to the pile for the digit 0, once again also based on a padding digit. So we now need to dequeue our values back into the data array. The first value is 5, then 11, which moves into the second position, then 20, then 25, and 77, and finally 315. So at this point, we see that these values have now been ordered in ascending order. We've also run out of digits that we can process. So we now have our array in a final sorted state, and as you can see here, we have the values in ascending order from smallest to largest. So that then concludes our entire application of the Radix sort algorithm to our example array. But I want you to consider this question. Do you think that it's possible to implement the Radix sort algorithm in a recursive fashion? So I won't give an answer to that now, but run through this example again and look at the operation from step to step and see whether there are any procedures that could be handled in a recursive fashion. We can use the Radix sort algorithm in a different way to sort a sequence of numbers, and this is by sorting the binary representations of these numbers. So in this example over here, we can see we have an array, and this array stores numbers, but they are represented then as binary sequences. So how we will then apply the Radix sort algorithm is by sorting according to B bits, starting once again from the right-hand side and moving to the left. So b then, in other words, is a parameter that we need to decide on. And in this particular example, b is 2. So you can see on the first pass of the Radix sort algorithm, we are sorting according to the rightmost 2 bits. Then for the next pass, we sort according to the 2 bits just to the left of the rightmost 2 bits. And so we continue until eventually on the last pass, we're sorting according to the leftmost 2 bits. So how many queues does this then imply we will be working with? Well, this obviously depends then on the value of b, and it boils down to the number of unique bit strings that we can represent using 2 bits. So for our example here, because b has a value of 2, this means we can form then 2 to the power of b bit strings, in other words 2 to the power of 2, which gives us 4 bit strings, which you can see over here, 0, 0, 0, 1, 1, 0, and 1, 1, and each of those strings is unique. This then implies that we need 4 queues. So over here I've outlined the 4 queues. So if we just look at the first pass of the Radix sort algorithm, we can see the first queue is contained over here. So it contains all of the binary numbers where the rightmost 2 bits are both zeros. The next queue over here contains all of the values where the rightmost 2 bits are the bit sequence 0, 1. Here we have a queue containing a single value, which has the rightmost 2 bits as the sequence 1, 0, and then our final queue over here, which contains the single bit sequence where the rightmost 2 bits have the values 1, 1. Right, so there turns out then to be a trade-off in terms of selecting the value of b. So the larger the value of b is, the more queues we have to process. So what this means is we have then additional wasted space because there's overhead associated with each queue. However, we will perform fewer passes because we are processing more bits at once for each pass of the Radix sort algorithm, so this saves on execution time. Conversely, for a smaller value of b, we then have fewer queues, so this saves then memory space, but we require then more passes, which will tend to waste more execution time. Over here we have a full implementation of the Radix sort algorithm, so let's run through it. At the top we have 2 constants defined. The first constant is called Radix, and that has a value of 10. This is because we are working with decimal numbers in the array that we want to sort. If we were working with binary values, then the Radix would have a value of 2. We also then have digits, and digits has a value of 10 over here, and this represents the number of digits that the Radix sort algorithm can expect to have to deal with. Then we have the actual implementation of our sorting algorithm, and we can see that it receives an array called data, which is the array that needs to be sorted. The first step then that needs to be performed is we need to create a list of queues. And this is exactly what we do over here. So we're defining queues, which is an array of queues that contain integer values. Now the size of this array then is equivalent to Radix, as you can see there. And this makes sense because there needs to be a queue for each one of the digits. And there are 10 possible digits within the decimal number system. So then we get on to this for loop over here, and this loop runs from 0 to 1 less than the Radix. So in other words, this for loop is running through each of the individual queues. And what this then does is for each iteration, it then initializes the queue at subscript d within the queues array, and it creates then a new queue that contains integers at that point. So now we've initialized our queues. Now we get into this loop over here, which is a for loop. The loop control variable is d, and it runs from 1 up to the number of digits. So this loop is going to run through each of the digits, and it's going to do so from right to left. So then we have this nested for loop over here, and this loop runs from 0 to 1 less the length of the data array. So in other words, it executes for every element contained in the data array. And what we then do is we retrieve then each element from the data array, and we enqueue that then into the appropriate queue in the queues array. The appropriate queue is computed by this calculation over here, and what this computation does is for the current value in the data array, it extracts then the appropriate digit, and it uses that as an index into the queues array. Following that, we have this second nested for loop over here, and this runs from 0 to 1 less than the radix. So again, this loop will execute once for each of the queues and associated piles. So this loop then has a nested while loop over here, and all that this while loop does is it checks to see whether the current queue is empty, and as long as there are elements contained within the queue, it then dequeues an element from the queue, and it then places it in the data array at the appropriate subscript. Right, so that's the complete algorithm. Let's now consider the efficiency of the radix sort algorithm. So again, we're going to decompose this operation by operation. And the first operation that we need to look at is this for loop over here. So this for loop runs from 0 to 1 less than the radix, meaning that every time that this algorithm executes, it will then execute exactly 10 times. What this means then is that the number of times that this for loop executes is not tied to the complexity of the problem that the radix sort algorithm has to solve. So in other words, the complexity then for this for loop is O1. In other words, constant complexity. The next component we have to look at is the second for loop over here, and this for loop executes from 1 to the number of digits. So in other words, this loop will execute as many times as the maximum number of digits for every particular number contained within the data array. In other words, the complexity then is OD, where D is then the number of digits that need to be processed. Then if we look at this nested for loop over here, we can see that it runs from subscript 0 to 1 less than the number of elements in the data array. So in other words, it executes n times, meaning that its complexity is On. And then when we look at this final for loop over here, well, we can see that this for loop is responsible for dequeuing every value that is contained within the queues and placing them back into the data array. So overall, this entire loops and operation, including then its nested loop, will run through all of the elements within the data array and place them back into that array. In other words, it will then execute n times, where n again is the number of items in the data array, meaning that its complexity is then On. So what is the total complexity? Well, we have 1 plus d multiplied by n plus n, or in other words, 2n in that case. Now we can discard the 1 because it's not a significant term and we're only interested in asymptotic complexity. And we can also eliminate the 2 once again because we're interested in asymptotic complexity. So what this means then is that the overall complexity is d multiplied by n, because this loop over here executes d times, and this loop, which executes n times, executes once for every iteration of this loop. Right, so that's the overall complexity. However, one thing that we haven't factored in yet is the complexity of the queues that we need to use. And what we've seen previously in this course is that queues are typically implemented as linked lists, and linked lists are not particularly efficient data structures. So this obviously then adds quite a large performance hit to the operation of our radix sort algorithm. And if we can somehow then eliminate the use of our queues, we can drastically improve the efficiency of our radix sort algorithm. So here we have then a fairly complex data structure which allows us to represent all of the data that the radix sort algorithm needs to work with, but it does this without the use of queue data structures in the classical sense. So we can see then that this approach works with three arrays other than obviously the data array that we're trying to sort. We have the queues array, the queue heads array, and the queue tails array. So the queue heads array then stores the indices of the first element of each queue, and this is then also the position where dequeuing will start in the data array. Then the queues array stores a linked list of data indices for each queue. Now, linked lists is in quotes over there because it is not actually a linked list data structure. It's actually a simulation of linked lists by means of indices that are stored within arrays, as we'll see in a moment. Then the queue tails array stores indices of the last element of each queue, and this is where in-queuing takes place in the queues array. So let's look then at two queues within this data structure. So the first queue that we'll look at is the one represented by subscript 0. So in other words, it's the queue for the digit 0. And we see that the value that is stored there is 0. So what this means is if we look in the data array at subscript 0, which is the value in the queue heads array, then we see that there is a value of 10 stored there. So this means that the first element that is stored in the queue for the digit 0 is 10. Next, we can look in the queues array at the same subscript 0, and we see that there's a value of -1 stored there. So this indicates that we've reached the end of the queue, and in other words, the number 10 is the only number that is contained in the queue for the digit 0. So let's then look at the queue tails array finally. Here again we're working at subscript 0, and we can see that the value stored there is 0, which means that the tail of the queue is located at subscript 0 within the data array, meaning that the last element is then also the same as the first element, which is 10. So this will then be the location that in-queuing will take place if we add another element to the queue for the digit 0. So let's look then at another queue, and this time we'll look at subscript 4 in the queue heads array, and we see that we have a value of 1 that's stored there. What this means then is in the data array at subscript 1, we have a value stored, and that is then the first value that is contained in the queue for digit 4. We can then also look in the queues array, and what we see then at subscript 1 is that there's a value of 3 located there. So what this means is there is then another value within this queue for the digit 4. So we see then that the value stored there is 3, which means for the next value we need to look at subscript 3 in the data array, and we see that that value is 7,234, which is then the second value contained within that queue. We can then look at subscript 3 in the queues array, and we see that there's a value of -1 that is stored there, indicating that there are no further elements within this queue. So in other words, we have two values in this queue, 1,234 and 7,234, and those both then fall within this queue. Finally, we can also look then in the queue tails array, again at subscript 4 over here, and we see that there is a value of 3 stored, which means then that the last value is stored at subscript 3 in the data array. And we can also then see that that element is indicated in the queues array by the value -1. So essentially what we have now is a representation of our queue structure. It's not represented, however, by an actual queue data structure, but we have, by means of the queue heads array, then very quick access to the point where we need to dequeue values from in the data array. We also then have, through the queue tails array, very quick and efficient access to the value that we will perform the next enqueuing at. So in other words, we will then determine that we now need to perform another enqueuing at this point, which will be then another value within the data array. So additionally then, we have this unnamed array structure over here. Now, the reason that this exists is that we can't dequeue directly into the data array. And the reason for this is that the data array contains the queue structures. So if the data array gets disrupted, then our queues get disrupted as well. So what we do then instead is we then maintain this additional array over here, and we dequeue into this array. And once we've finished dequeuing all of our values into this array, then instead of copying these values into data, we just simply set data to point to this array. And then we dequeue into this array over here, and then switch to it for the next iteration. So essentially what happens is we then bounce back and forth between the data array and the second array, and we don't need to then perform any additional copying operations, which will take up additional time. This concludes our discussion on the Radix sort algorithm. So we will now move on to the counting sort algorithm. So over here we have an array of integer values that we want to sort, and we can make the fairly trivial observation that array indices are always sorted. So in other words, array indices always start off at 0, they increase by 1 at each step, and they eventually stop then at size -1, which is 7 for this example. So what if we treat then each element in this array as an index into a target sorted array? So over here we've defined our target sorted array, which we will call temp, and the last index of this array must then be the largest data value. So if we look through our unsorted array, we can see that the largest value here is 7, which means that the last index or subscript must be 7 within this temp array. In other words, it must contain 8 values. Right, so now we need to populate the array. So we run through then each subscript within our source unsorted array, and that subscript is called I. We retrieve the values stored at subscript I in the data array, and then we set temp's value at subscript array at subscript I to this value that we've retrieved. So let's look at what this looks like. We start off with subscript 0 in our source array. We see that the value there is 6. So this means we need to store the value 6 at subscript 6 in the temp array, as we've done there. Then we move on to the next element. So now we need to store the value 7 at subscript 7 in the temp array, which we've done over there. Then next we need to store the value 2 at subscript 2 in the temp array. We do then for 5 the same thing. So 5 is stored at subscript 5, 1 is stored at subscript 1, 0 is stored at subscript 0, and 3 is stored at subscript 3, and then finally 4 is stored at subscript 4. So now we can see we've ended up with a sorted array. Now this may seem like a fairly trivial example, and it's trivial because the values that are stored in the original source array run from 0 up until 7, and they are not separated by gaps. But we can use the general idea behind this approach to construct a more robust algorithm, which we will call the counting sort algorithm. So there are two outstanding questions at this point. What if there are duplicate values within our unsorted array? How do we deal with those? And secondly, what if there are gaps between numbers? So in other words, numbers do not just increase by 1 from the previous value. There are potentially larger gaps between subsequent numbers. So here we have the pseudocode for an implementation of the counting sort algorithm that addresses the two problems we mentioned on the previous slide. So you can see that we are sorting an array called data over here. And the first thing that we need to do is we need to count the occurrences of each unique number within the data array and then store these occurrences in an array called count, and they will be then indexed with the numbers in the data array. So over here we have our count array. Now notice that, as in the previous example, the last index within the count array is 9, which is also the largest value within the data array. So in other words, the count array then contains, for this particular example, 10 values. All right, so now we need to iterate through the data array, starting at the first element, and we need to then update the count at that subscript within the count array. Notice that the count array has been initialized to contain only 0 values. So for the value 7 in the data array, we update the count for 7 in the count array. Then for the next value in the data array, which is 2, we update the count for 2. We do the same for 9, so we've incremented 9's count to 1. Then for 3, we also increment the count to 1. Then for 7, we need to increment the count again, and we see that the count in the count array at subscript 7 is 1, so we increment it to 2. For 3, we also need to increment the count. Once again, it's incremented from 1 to 2. Then for 4, we increment the count in the count array to 1. And finally, for 1, we increment the count to 1. So now we've stored the number of occurrences of every particular number within the data array. So next we then need to enter this for loop over here, and this for loop runs from index 1 up to 1 less than the number of elements in the count array. So in other words, starting at subscript 1, we run all the way to the end of the count array, and then we set the value at the current index in the count array to the number of elements that are less than or equal to i's current value. Right, so let's look at what this would look like. Here we've just duplicated the count array just to illustrate our example. So we begin then at subscript 1. And now what we do is we update its count by taking its current value and adding it to the value stored in the previous index location. So in other words, in this case, we are adding 0 to 1, and this gives us then a result of 1, meaning that the value at subscript 1 in the count array does not need to change. We then move on to the next value. So now we are adding the previous value of 1 to the value at the current subscript, which gives us a result of 2, which we then update there. We move on to the next value. So now we're adding the value 2 to the current value 2, which gives us a result of 4. Then we move on to the next value. So now we're working with 1. So we add 1 to the previous value, which was 4, giving us a result of 5. And so we continue through the rest of the array. So the value at subscript 5 is updated to 5. 6, it's updated to 5. 7, we update the value from 2 to 7. 8, we have a value of 7 because the value stored at that subscript is 0. And then finally for 9, we add 7 and 1, which gives us a value of 8. So at this point, we've now initialized our count array. So this is the current state of our data array and our count array. We also now create a temp array. And this then has the same number of elements as our data array, but it's currently unpopulated. So now we need to enter this for loop within our counting sort algorithm. And this runs then with our loop control variable I from n-1 down to 0. So in other words, we are iterating from the last element in the data array all the way down to the first element. What we then do is we update the temp array. We need to retrieve an array from the count array, which is the value stored at the current subscript of the data array. And then we subtract 1 from that value that we retrieved from the count array. And at that point in the temp array, we then place data's current value. So let's look at what this looks like then in practice. We start off then with the last element in the data array. And we see then that the value located at that subscript is 1. So we then look in the count array at subscript 1, and we see that we have then a value of 1 stored there. So now what we do is we decrement this value in the count array, which we've retrieved, which is 1, and that gives us a value of 0. And now the value in the data array at the current index is then updated at that subscript of 0 in the temp array. So that's what we've done over there. So then we also need to decrement, once we've performed the copy of the value into temp, we have to decrement then the current value in the count array that we've retrieved. So in other words, we then decrement this value 1 and then move our pointer in our data array to the next element. So that's exactly what we've done there. We've decremented the 1 to 0, and now we're pointing at the next element in the data array. So then we just keep repeating this process. So now we have a value of 4 in the data array. We look at subscript 4 in the count array, and we retrieve a value of 5. We then subtract 1 from that, so that gives us an index of 4 into the temp array, and we then copy the value in data to that location. So now we move the pointer in data along by 1, and we also have to decrement the value in the count array that we retrieved. So we've decremented it from 5 to 4, and we're now pointing to the value 3. So once again, we then retrieve the value from the data array, which is 3, and we look in the count array at index 3, and we retrieve a value of 4. We then subtract 1 from that. So that gives us then a value of 3, meaning that we are now updating the value in the temp array at subscript 3 with the current value in data. So that's the result. We now need to again decrement the value in the count array that we're currently at and move the pointer in data along. So that's exactly what we've done there. We've decremented the value from 4 to 3 in the count array, and we are now pointing at the value 7 in the data array. Again, we retrieve the value 7, so we refer to the count array at index 7, and we retrieve the value 7. That means we have to then update the temp array at index 6. So we copy the value 7 to index 6, move our pointer along to the next point in data, and also then decrement the current value in count that we've retrieved. So we've done that over there. Now we retrieve the next value in data, which is 3. So we're accessing the count array at subscript 3. We subtract 1 from that value that we've retrieved. So now we're updating the temp array at subscript 2, and we copy the value 3 into that location. We move the pointer in data along, and we also decrement the value in count that we're currently looking at. And now we retrieve the value 9 from data. So now we're looking at, once again, index 9, again in the count array, which retrieves a value of 8. We subtract 1 from that, which gives us a value of 7. So now we're updating the temp array at index 7, and we copy the value 9 to that location. Now we move our pointer along again, and we decrement our value that we're currently looking at in the count array. And now we move on to the next value within data. So now we retrieve a value of 2. We access the count array at subscript 2, which gives us a value of 2. We subtract 1 from that, which is 1. So now we're updating the temp array at subscript 1, and we copy the value 2 to that location. So now we're almost done. We move our pointer in data along again, and we decrement the value of 2 in our count array. And now we are looking at the value 7 in the data array. So we retrieve then in the count array the value at index 7, which is 6. We subtract 1 from that, which is 5. So that's the location that we update in the temp array, and we copy the value 7 to that location. We've now moved through the entire data array. The only step that is required is that we have to decrement the value of 6 in the count array. This gives us then our final count array, but most importantly, we now have a fully sorted version of our original data array. Let's now turn our attention to a complexity analysis of the counting sort algorithm. So the first component of the counting sort algorithm is over here, and this is responsible for counting the number of occurrences of each number in the data array and storing those occurrences in the count array. Now this of course requires a full iteration over all of the elements within the data array, which means that we will then be performing n steps, meaning that the complexity then of this portion of the algorithm is O(n). Next, we need to consider this for loop over here. So this for loop runs from subscript 0 to 1 less than the length of the count array. Now, what we saw in relation to the count array is that the length of the count array is determined by a maximum number of digits, which is found over all of the numbers contained within the data array. So how many times then will this loop execute? Well, it will execute then approximately the length of the count array, which is determined by this maximum digit count. So the complexity then of this portion of the algorithm is O max, where max is the maximum number of digits found across all of the various numbers that are contained within the data array. The next portion that we need to consider is this for loop over here, and as we can see, it runs from subscript n-1 down to 0. In other words, it iterates backwards through the data array from the last element to the first element. So fairly obviously then this loop must execute n times, which means that its complexity then is O(n). This final operation here is typically performed because we usually want to take our temp array, which contains our sorted array, and we want to get those values back into the data array again. So once again, this requires a full iteration over the data array and the temp array, and both of those arrays contain n elements, which means the complexity of that portion is O(n). So what is then the total complexity? Well, we just add then these various complexities because they follow one another. So we have O(n) plus O max plus O(n) plus O(n). Or in other words, we have 3n plus max. Now we can discard then the 3 because we're interested in asymptotic complexity, which then means that our overall complexity is O(n) plus max. Now this is an interesting result because the complexity depends not only on the number of elements within our data array, but also this max value that we determine over all of the numbers within the data array. Now let's consider a specific example then. Here we have an array with 3 elements in it, and we can see that 2 of the elements have very few digits. In fact, they each only have 1 digit, but we have 1 element with a large number of digits. Now, as we know, this very large number then determines the value of max. So what this means is that this array's structure and the fact that we have this very large value that is contained within the array is going to have then a large detrimental impact on the performance of the counting sort algorithm. In fact, what will happen in this case is that the value of max will completely dominate n, because in this case n is only 3. So what this means then is that counting sort is very efficient, but only generally if max is not much larger than n. In other words, max should not dominate the complexity that we compute. So a last question then related to the counting sort algorithm is, can counting sort work for non-integer values? Now the answer to this is based on how the values within the data array are used. And we saw that these values are used as subscripts in other arrays. What this means then is that counting sort is designed to work with integer values specifically, and it's not very well suited to work with non-integer values. We've now discussed a fairly large number of sorting algorithms. So the question then that one should ask at this point is, which of these algorithms should we use in practice? And the answer to this question, unfortunately, is not easy. So over here we have an extract from a larger table that is in the textbook. And this summarizes the results of applying a variety of different sorting algorithms to lists and then timing how long these algorithms take to sort these lists. So for this particular extract of the table here, we're sorting a list that contains 80,000 integer values, and we order then these values in different ways. So we have the values in ascending order. In other words, we're applying the sorting algorithm to an already sorted list. We have a list that is in random order, and then we have a list that is in descending order. So if we look at these results, we can see a few interesting things. For each column, we have highlighted the lowest value in blue. This indicates the shortest amount of time, so in other words, the best performing algorithm for the particular list in question. We also then have the second best performing algorithm listed in green, and then in red we have the worst performing algorithm out of the entire set. So if we look then at this table, we can see there's quite a lot of variation in performance. We would generally expect that an algorithm should perform very well on a list that is in ascending order because it is already sorted. But this isn't necessarily the case. So for example, if we look at Radix sort over here, we can see that sorting the ascending order list takes longer than both a random list and a descending order list. We can also see that for the most part, the elementary sorting algorithms, which we have over here, perform incredibly poorly. You can see that they take a couple of minutes to finish sorting this list of integers. However, interestingly, insertion sort takes a very short amount of time to sort a list into ascending order. So essentially the take home from this then is that the algorithm that you select very much depends on the specific application that you are attempting to perform a sort within. So you need to understand how the algorithm performs, what kinds of data the algorithm will have trouble with, and conversely what kind of data the algorithm will perform well on. The only thing that we can really say for sure is that one should always avoid the simple elementary sorting algorithms. So that concludes then our entire discussion on sorting algorithms, and we will begin with the next chapter in the next set of lectures.